What we are going to study today is kinematics, which is a branch of mechanics, which in turn is a branch of physics. Mechanics is that branch of physics in which we study motion. In general, we study motion. Then within mechanics we have two major branches. One is kinematics and the other is dynamics. In kinematics we study motion mathematically, or in other words we study the mathematics of motion without any concern or without any study of the cause of this motion. Later, when we study dynamics, we study what is causing the motion along with the study of motion. So kinematics, which we are going to start studying today, is a study of motion, or rather the mathematics of motion. Here we will not be worried, we will not bother ourselves with the cause of the motion. We will only have a mathematical study of motion. And in this study, the first thing we need to kind of discuss is well, what constitutes motion. Let's have a general definition of what is motion. Generally speaking, motion is a term we use to describe the changing of position of an object along with the passage of time. So if time is passing and the position of an object is changing with reference to maybe the surroundings, then we say a motion is taking place. But since we are studying physics and we like to be more precise, instead of using the term surroundings, we will have a slightly more accurate term which we will be making use of, and that term is frame of reference. Now, generally speaking, frame of reference is the surroundings with respect to which we study motion. But then in physics we like to study everything by studying the mathematics of it in very precise terms. Therefore we need to formalize this surroundings term, and therefore we replace it by the word frame of reference, which then constitutes a set of coordinate axes in which we study the motion of an object. Now, how do we study motion of an object with reference to a set of coordinate axes? What we do is we pick up a surrounding object, and on that object we attach three coordinate axes, the x-axis and the y-axis. Now these are two coordinate axes, x and y, which I can draw within the plane of this board. And then there is a z-axis which is perpendicular to the plane of the board. Now it passes through this point, the origin, and is perpendicular to the plane of the board outward like this. Now what you can visualize about z-axis is you can hammer in a nail here, tie a thread to the nail and pull the thread out perpendicular to the plane of the board. Now this thread, as it's been pulled out perpendicular to the plane of the board, is perpendicular to both x and y axes, and this perpendicular thread now constitutes the z-axis. Ideally speaking, the z-axis cannot be drawn on this board, so what we really do is we kind of draw a shadow of the z-axis over here, and this shadow represents the z-axis. How you need to visualize it is you need to think of it as a line perpendicular to the plane of the board and coming outward from the board. Now this set of coordinate axes have been fixed to some surrounding object. We are going to observe the motion of some other object in this set of coordinate axes. Now this is, let's say, the object whose motion we are studying, and we reduce any object to a point, generally speaking. Now why we do that is because if we have a large object, say for example a car, the motion of the entire car can be a little complicated. I mean, the wheels are rotating and the car is moving forward, it may be jumping up and down. The motion can be a little complex for the entire vehicle, but very often what we can do is we can fix up a point on that car, let's say a door handle or something, and we study the motion of that door handle, and then we make an assumption that the motion of the entire car is identical to the motion of the door handle. This process is called reduction of the moving object to a point, or what we've done is we've reduced the moving object to a point object. Now we cannot always do this, but more often than not we can. The only conditions required for reducing an object to a point object is that the size of its motion should be small in comparison to the size of the motion should be large, rather, in comparison to the size of the object. Say for instance, a train is moving from a station to the next station, and the next station is only about 1.5 kilometers and the train is 500 meters long, then the motion cannot be reduced to that of a point object. But we can reduce this motion to a point object if the same train was to travel, say, a few thousand kilometers. Then we can fix a point on the train and study the motion of that point. It would then represent the motion of the entire train. So an object can be reduced to a point object if and only if the size of the object is very small in comparison to the size of the motion. Also, this point object assumption can be made if the object is not rotating and there are no major jerks in the motion. Now, let's say we've reduced our object to a point object. Then its position is defined by its coordinates. The object will have x, y, and z coordinates. Now, these coordinates can be easily described as, the perpendicular distances of the point from various planes. For instance, this is the xy plane. The plane of the board is the xy plane. If from this point I drop a perpendicular on the xy plane, that length of the perpendicular would give me the z-axis. So if I take the xy plane, I drop a perpendicular from the point onto the xy plane, the length of that perpendicular is the z coordinate, and you can then similarly define the other coordinates. Now, if we have reduced the object, the moving object, to a point, and we are now studying the motion of this point, then the next thing that comes to our mind is whether the object with respect to which we are studying the motion is itself at rest or it is in motion. Typically what we do as ordinary people is that we assume that the object with respect to which we are studying the motion is at rest. Now in physics, as we explore things more and more, we will discover that there can be no such thing as an object at rest. But to start with, to keep things simple, we assume that this object is at rest and we are looking at the motion of this object. This set of coordinate axes becomes our frame of reference with respect to which we are studying this motion. So, just to keep things simple for now, we are assuming that this object is at rest, so these axes x, y and z are also at rest. In a general kind of motion, all these three coordinates might actually be changing, and that would be the most general case of motion. But then that most general case of motion is a complex one, and we do not start studying complex things right away. We will be studying the simplest possible case of motion, and that is motion along a straight line, which would be called one-dimensional motion. So we are starting our study with the motion along a straight line, or what one might call motion in one dimension. Now when we do this, when we study motion along a straight line, we are looking at an object which is moving purely along a straight line. Now when motion is purely along a straight line, that straight line is described as the x-axis. Now we can very well choose to call it the y or the z-axis, but conventionally what we do is we treat that straight line as the x-axis. This is just a convention, or you might say this is just a tradition, that the straight line along which an object is moving is described as the x-axis. On this x-axis, we have to decide about the positive x and the negative x-axis directions. The choice is a totally arbitrary one. We can describe any one direction as positive x, and the opposite direction can then be described as negative x. Any point on this straight line can be assumed to be the origin. Now when an object will move along this straight line, what we do is, when we start our observation, suppose we start our observation at a particular point of time, at that point of time the position of the object is given by x0, that is the x coordinate. This observation takes place at a certain point of time. Now, what do we call this point of time, or what do we describe this point of time as? Well, when we start studying motion, immediately we turn on a stopwatch. So we have started observing this motion. The object is here as of now. This is the x coordinate, x0. The observation is made at time equals 0. That's what the stopwatch will show immediately after it is switched on. So at time equal to 0, this is where we have observed our object. So as the object now moves, we will be looking at various things about its motion. Now as time passes, the object moves, let's say, in the positive direction of x-axis. As time proceeds, the object moves in the positive direction of x-axis. Now remember, in the positive direction of x-axis, if there is a motion taking place, then any vector, I'm sure you have some amount of familiarity with the term vector from perhaps class 9 or 10. When we described vectors. These are physical quantities having directions. Now there are certain vector quantities that we use for describing motion, and we will talk about them as time proceeds. All vectors that are used to describe motion, if they are in the positive direction of x-axis, we will describe them as positive. All vectors which are in negative direction of x-axis will be represented as negative quantities. So vectors in positive direction of x-axis will be taken as positive. Vectors in negative direction of x-axis will be taken as negative. And that's the sign convention that we will be following in our study of straight line motion. Now let's make an assumption that when we started our motion, when we started our study of motion, the object was at x0, and that's when we turned on the stopwatch. Now we kept observing this motion, and the object kept moving in the positive direction of x-axis, and when it reached a position, say x1, we assume that the time was equal to t1. Now I'm just simply describing a very simple example of motion, and then we will talk about it at length and understand a few basic terms regarding motion. Now, so this object starts moving here at time equal to 0 from x0, and at time equal to t1 it is observed at x1. Now these are times that our stopwatch is giving us. It comes here, it stops momentarily and starts moving in the reverse direction. And then we observe that at time equal to t2 by our stopwatch, the object has reached this position where the position or the x coordinate is x2. So this is the motion that we are talking about. The object started here at time equal to 0 at x0, it reaches x1, stops momentarily, reverses direction and reaches this position where the coordinate is x2. The time here was 0, the time here is t1, and then further the time here is t2. Now since motion can be forward or backwards, but time does not move back, so t1 is of course greater than 0 and t2 is a greater amount of time than t1. Now I'll be describing a few very basic terms which are used in describing motion in general. The first one of those terms is called distance. What is distance? Distance is the length of the path, or the path length in motion. The length of the path in a given motion. This distance is a scalar quantity. Now from your junior classes you all know that scalar quantities are quantities which do not have any direction, and therefore they are simply represented by numbers, and they are also added and subtracted like numbers. So the algebra for study of these scalars is very simple. Distance is simply the length of path and it does not have any direction. It's a scalar quantity and it can never be negative. It's always a positive quantity, since there is no notion of a negative distance. Distance can only be positive. And as I said, it's a scalar quantity. Now the next quantity that we talk about is called displacement. Now this quantity is a vector, which basically means it has a direction, and it is described as a vector drawn from initial point of motion to the final point of motion. Displacement, as I've said, is a vector drawn from the initial point of motion to the final point of motion. Now in this particular case, if I were to describe displacement from time equal to 0 to time equal to t1, then that displacement would be a vector drawn from this point all the way up to this point. So let's just redraw this axis. This is x, positive x, origin. This is negative x, and here is x naught. The particle was seen here at time equal to 0, and then at time equal to t1, the particle was seen here. We draw a vector from this point all the way up to this point, and this vector represents displacement. Now the length of this vector represents its magnitude, and the arrow represents direction. And since this particular displacement is in positive direction of x-axis, it is a positive displacement s. Now this displacement s can easily be expressed as the final position here, x1 minus x naught. So displacement can easily be described as the final coordinate minus the initial coordinate, or final position minus the initial position. Now since the object was moving in the positive direction of x-axis, the x coordinate was increasing, so x1 is greater than x0, and therefore the difference will be a positive difference. So displacement s here is a positive displacement. It is in positive direction of x-axis. If the object had been moving in the opposite direction, then the final coordinate would be less than the initial coordinate, and therefore displacement would have been negative. So the convention we have described earlier works pretty much okay, even with this description of final coordinate minus initial coordinate. So we've described two quantities here, distance and displacement. Now we'll study something very important, very critical about distance and displacement. Let's have a look at the values of distance and displacement during the various intervals of time. So first interval of time I'll be looking at will be from time equal to 0 up to time equal to t1. So the first interval I'm having a look at is from time equal to 0 to time equal to t1. In this interval, the distance simply happens to be the length from here to here. Distance is the length of the path. If you recall, it's the length of the path. So the length of the path from here to here is simply x1 minus x0. Mind you, distance is a scalar and it cannot have negative values. There is no notion of a negative length of path, and therefore we use the mod sign here. This mod tells us that the distance can only be positive. So if in some calculation the final coordinate minus initial coordinate happens to be negative, by taking the mod we've made it positive. So that's distance in this motion. The displacement during the same interval of time, the displacement during that same interval of time is x1 minus x0, which in this case happens to be positive anyway. So here what we have noticed is that the distance and the displacement are both equal. Now let's move on and study the next interval from time equal to t1 to time equal to t2. So we are having a look at this interval now, time equal to t1 to time equal to t2. During this interval, the final coordinate is x2. From that we subtract the initial coordinate, that's x1, and then we take a mod, and that's the distance, the length of the path from here to here. Now during the same interval, the displacement will be the final coordinate minus the initial coordinate. The final coordinate minus the initial coordinate, and as you notice, the final coordinate x2 is less than x1, and therefore x2 minus x1 is negative. The displacement is in the negative direction of x-axis, and therefore it is negative. Now you might say the motion is happening on positive x-axis, but the direction, the sense of direction of the motion from this point to this point is along the direction of the negative x-axis. So since this sense of motion is along negative x-axis, this displacement here is negative. Distance is a mod, it's a magnitude of this length, and therefore it cannot be negative. It's a positive quantity always. Now the distance here and the displacement differ only in the sense that this has a negative sign while this is always positive. Over here, this is the displacement, it's positive. The distance is anyway always positive, so there was no difference really. But something very interesting happens when we look at the entire motion here. If you look at this entire motion starting from this time 0 all the way up to time t2, so we are now looking at this interval from time equal to time equal to 0. We're looking at the interval from time equal to 0 to time equal to t2, and that's the entire motion. Now in this entire motion, when we look at distance, that's the length of the path, it is this length plus this length. Now essentially we will be adding these two lengths, and that will be our distance. So x1 minus x0 plus x2 minus x1. The sum of these two distances, these two lengths, when added, give us the total distance. Now when we look at the displacement for the same interval, it is simply a vector drawn from the initial point of this motion all the way up to the final point of motion. This vector, which is x2 minus x0. Now this happens to be positive here, but you will notice very easily that this displacement has a magnitude or size which is very different from this magnitude. An interesting, very interesting and very important observation in this, that whenever the direction of motion undergoes a change, whenever the direction of motion is changing, the object was first moving in positive direction of x-axis and then started moving along the negative direction of x-axis. In such cases, wherever there is a change in direction of motion, distance will always be greater than displacement. So if motion direction changes, then distance will always be greater than displacement, or rather magnitude of displacement. But if there is no reversal in motion direction, the magnitudes of distance and displacement remain the same. There is no change, there is no difference between their magnitudes. As you can notice in these two examples, the magnitude of distance and the magnitude of displacement, they are same. But the moment you have a motion in which motion direction is changing, initially the motion was in positive x and then it was in negative x direction. Whenever there is a change in motion direction, distance ends up having a magnitude which is greater than that of displacement. So this was an introductory discussion on straight line motion and the sign convention we use and the concepts of distance and displacement. In our next video, we will study about average speeds and average velocities as well. Also, after that, we will be studying some calculus, which is a very interesting branch of mathematics, of course, at a very basic, at a very cursory level, so that we can handle the remaining physics or the mathematics of the physics that we're going to study. Thank you very much.